Oh, whoops, I never turned on music or whatever. Hi. This is literally 45 seconds after I finished the previous video, which ended up taking forever in a day. I think it's like an hour long. Feel free to not watch it. I won't be offended. If you only watch one of them, you should watch this one. Okay? And I say that now. Okay? I'm doing another ecological interaction. This one is a bit easier. Okay? The XDT, I want to say, grows logistically. So in the absence of the other species, it just goes hog wild up to K, and then it gets et by the other species. Okay? Now, dy dt, which is going to be my predator here in this case, right, cannot survive without species X, and it needs it. It consumes it, comme ça. All right? So automatically the equations are quite a bit simpler. So my equilibria are going to be simpler because the algebra is just going to be much more tame. Okay, this is parasitism. Okay, specifically predator prey. Yeah, let's just get to it. Okay, let's just get to doing the work. All right, I'm going to sit like this so it's all nice and personal. So it looks like I'm just hanging out with you and we're working together in the library or something, even though there's a blasted wasteland behind me. What's the first step? Find equilibrium. I like I'm doing it like a children's cartoon. Like, can you spot the fallen tree? Like I'm Dora the Explorer. All right. Fix points. So let's set Rx times 1 minus x over k minus exy equal to 0. Okay? We're going to break it up into cases that we're going to notice. First off, that x equals 0 by factoring it out from both of those terms. One of them's there, one of them's... I thought my pen died. Or r minus r over kx minus ey, geez Louise, equals 0. And you might already be having panic attack flashbacks because this looks very similar to what we had last time. But don't worry, because the y prime equation is much simpler. It'll be okay. All right. Let's use the x equals 0 fact here. Okay. So I've got negative sy equals 0. So this implies that y equals 0. So we've got the origin is our first fixed point. Awesome. The origin's always nice because it's relatively beautiful when you plug it into the Jacobian. Everything cancels out and it's awesome. Okay. Now this fact right here, let's go ahead and preempt with something. Let's solve for y equals r over e minus r over ek x, and then we take my s prime or y prime equation, and I'm going to rewrite it as y times cx minus s equals 0. So either this equals 0 or that equals 0. Those are the only two options, right? This first one implies that r over e minus r over ek x equals 0, which gives me that x equals k, which should make sense, and y equals 0. There's my second equilibrium point. Hey! Okay, finally, we get from here, hey, there's no y. This becomes much easier, right? Unless I wrote something down wrong. No, I didn't. Okay, great. X equals S over C. I'm so tired. I'm so punchy. It's 1 o'clock in the morning. So y equals r over e. And this was the day that all my students watched me lose my goddamn mind. Okay, right there. Just doing a tiny bit of algebra. We're going to get the equilibrium point S over C, comma, R over E multiplied by CK minus S over CK. So I got 3 equilibria. Okay. We want to calculate their stability. We got to do Jacobian work. All right. So again, that's the linearization business. Lin. That's all I'm going to write because I don't want to write anymore. Okay, great. So what we're doing is we're taking the partial derivatives of the various functions and organizing them into a matrix. Take a look at your notes. The partial derivative of the logistic growth with a harmful competitive term on there gives me r minus 2r over k x minus ey minus ex cy negative s plus cx. Okay, so that's the general form of the Jacobian. This in and of itself doesn't matter. We need to evaluate it at our equilibria. The first equilibrium, which is always the easiest to evaluate at, is the origin, r, 0, 0, negative s. What kind of equilibrium is the origin? I'll wait. We can read off our eigenvalues rather easily as r and negative s. So one is positive, one is negative. They're both real. That's a saddle node. We could also do it by noting that the trace is r minus s, which I don't know if that's positive or negative. Wow, that was really delayed. Or the determinant is equivalent to negative rs, which we know is negative. As soon as the determinant's negative, you know it's a saddle node. Okay? Fantastic. This is a saddle. And for some reason, I always write saddle in all caps. Don't know why. Now, the Jacobian at my next equilibrium point, which was K0. So this is when species X is at its carrying capacity and there's no species Y to speak of. I'm going to get negative R, negative EK, 0, and C minus SK. Seems pretty good. So I get for eigenvalues negative R or C minus SK. Those are my two eigenvalues. One of which is always negative, so I know I'm stable in one direction. And then, so I know I am stable. I don't know if it's node, or actually I do know it's a node, it's a stable node. If C minus SK is negative. I know it's a node because I can't get complex values here. They're not complex conjugates, so I know it's not a spiral. Okay, or a saddle if C minus SK is positive. Keep that in our brains. Okay. The last equilibrium point is, I got it written down on a piece of paper. I'm not going to try to memorize that because that would be really hard. Okay. Plugging that all in the matrix at the other equilibrium. Please do that on your piece of paper. Pause the video and then come back to see if we match. Negative RS over CK. Negative ES over C. R over E times CK minus S over CK. 0. Sadly not triangular. All right. I argue, again, solving the characteristic polynomial in this case would be needlessly troublesome. Let's just look at trace and determinant plane. Okay. My trace here is negative RS over CK. So I know, like if I'm thinking about my trace determinant plane, okay, I don't care about any of this. So I'm either a stable spiral, a stable node, or a saddle. Of course, I could be one of the boundary conditions, but probably not, right? All right, so that's what I'm faced with right now. So let's take a look at the determinant. All right, the product of my diagonal elements is a big fat 0. And so I'm going to subtract from that the product of my off-diagonal elements. And so I get SR over C times CK minus S over CK. And once again, in beautiful form, uh-oh. Is that right? You're getting the real experience of being in class right now where I'm like, whoa, that looks different than the other thing. Because the other one had SK and this one has CK. And I have too much paper. This third equilibrium would not be biologically valid if that was true. That's fine. That's that. That's something different. That's something different. Just throwing stuff away now. CK, not SK. Oh, did I make a mistake up here? Definitely made a mistake that no one called me out on. Why didn't any of you raise your hands? Right here. This right here should be CK minus S. Okay. And so these conditions just change ever so slightly to it's a stable node if, let me go ahead and erase that because that's wrong. CK minus S. Stable if this is negative, and it's a saddle node if this is positive. So we come down here, we get the exact same sort of conditions where my determinant is negative if CK minus S is negative. So this is a saddle if CK minus S is negative, and it's stable if CK minus S is positive. Cool. All right. Let's just work with that as our two different cases, okay? So case number one, CK minus S. Let's go ahead and make that positive. Okay, that's going to be our very first case. And I'm going to draw an axis here. Boop. Boop. Where this is X and this is Y. So we have three equilibrium points. Let's go ahead and utilize colors here. The origin is in equilibrium. K0 is in equilibrium. And then let's take a look at what the coordinates are for our last one. It's this right here. Okay. S over C. I'm just rewriting it. S over C, comma. Lost them. There we go. R over E times CK minus S over CK. Should not have done that red, but that's okay. All right. Now, if CK minus S is positive, then this coordinate is certainly positive. This one is also positive. So I've got a third equilibrium up here somewhere. All right. I guess we don't know where it is in relationship. We need to know how S over C relates to... Oh, we do. Yeah. How does this relate to K? Right, because this coordinate right here is K. All right. Well, if CK minus S is positive, then that means that K is greater than S over C, which means I am certainly to the left of that equilibrium. Everybody with me on that? I hope so, because that was cool. Okay? All right. Now, my origin here, if we're in this case, my origin is a saddle. This axis equilibrium is a saddle, and this equilibrium is stable. Okay, so to fill in these blocks, the easiest one to fill in right now is that this one's stable. So everyone near him needs to be pointing at him. Okay, which means that my origin has to at least have a trajectory that's pointing out toward that. So far, so good. And it also means that on my axis, that equilibrium has to have somebody pointing out toward them. Now, what that means is that you have to have somebody pointing in here. Things are about to get really ugly. Okay. What I'm doing here is I'm trying to fill in information that would make sense. Okay. This is a bit tricky here because what I actually wrote was just completely and utterly wrong. Okay, we need to know how the other arrows fit in here, and this can be really tough, right? But if we think about y equals 0, then x prime, whoops, if y equals 0, then x prime is merely rx times 1 minus x over k. We know how that behaves. We know it goes like this and like this, right on that axis. Okay, so we know those have to be the attracting directions, which means that this is probably not the eigenvector that sticks out, that it is in fact this guy over here. But that's okay. Now, if there's no x, that means that y prime is simply equal to negative sy, which means I'm decaying along this axis here. So I know I look something like this. That's my saddle at the origin. And I know my saddle on this axis here does this. And I know I shoot out like that. We get some ketchup and mustard going on. So how does this all fit together? Let's say I'm up top here. I'm going to come down. Oh, and I just get sucked in because that's really close. Okay. Let's say I'm over here. Oh, I'm going to get pushed down. Oh, but then eventually I'm going to get sucked up in. So something like that for right up there. Seems pretty good, right? Let's start way over here. I'm going to get pulled in by that red saddle, but eventually, oh, I'm going to get pushed out and then sucked in by the pink. Cool. With this pink, boop, 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 boop. That all makes sense. Okay. Now, what's happening in here? Well, I'm going to be pushed away from the orange saddle a bit. Oh, but I'm also going to be pulled in by that red saddle and then eventually chucked out. And so I get something that looks like that. That makes sense to me. Did it make sense to you? Cool. Case number 2 is CK minus S is negative. Now, while this isn't necessarily biologically relevant, well, a part of it isn't biologically relevant, but this whole case is biologically relevant, okay? If we do this out, I still have an equilibrium at the origin. I still have an equilibrium at 0K. But now I have an equilibrium whose y coordinate is negative and whose x coordinate is greater than k. So I know I'm over here somewhere. Okay? Now, in this case, whoops, my origin is still a saddle. It's always a saddle. This guy right here, that's a stable node. And then this last point down there is a saddle. Okay? Using extremely similar arguments to when there's an absence of species X or an absence of species Y, I know that this saddle looks like this. And I'm drawing arrows just very close to it. Okay? My red point I know is a stable node. So near it, I just all flow goes to it. Okay? Let's try to start filling in trajectories to see what we can see. So this is the saddle push-pull from the orange, leading it off into the red. That's just plain old attraction into the red. And everything in between just behaves quite nicely. Cool. Over here, we just get the push-pull from the saddle. No problem. Push-pull from the saddle. Now over here, we've got the weird case of 2 saddles. Now we don't know how this one necessarily behaves, except I do know that I need to push toward that red. Because if I pull away from that red, then we're tearing apart fabric of reality business here. So I know I'm pushing toward it, and let's go ahead and put it opposite there. Okay, so that would mean that somewhere in a different direction, it doesn't have to be perpendicular. I have to be pulling. Those two make jolly good sense. Now what's tricky is in this intermediate region here. Go ahead and grab blue. Okay, I'm probably flowing like that. Oh, but eventually one of these is probably going to get sucked in and go like that. Okay, that's fine. I can fill in all that intermediate area. But then there are others that get sucked in and pulled off down there. Cool. That makes sense to me. I hope it makes sense to you. I hope all this makes sense to you. I'm overtired. Make another video with an epidemiological example. Where's the button?